Hello everyone, I welcome you all in module 3 of course Mechanics of Solids, and in this particular module we are going to discuss about bending stresses, shear stresses and torsion. So to start with we are discussing part A of this particular module, that is bending stresses. If a member is subjected to equal and opposite couples acting in the same longitudinal planes, the member is said to be in pure bending. If a constant bending moment without any shear force acts on same length of a beam, the stresses developed or set up on any cross section on that particular part of the beam constitute a pure couple, the magnitude of which is equal to the bending moment getting developed at that particular cross section. The internal stresses developed in the beam are called as flexural or bending stresses. So, if you go through this particular diagram, figure 3.1a, so this is a simply supported beam supported at A and B, and say it is subjected to point loads W at distance A from support A, and again a point load W at point D at distance A from another support B. So if span of that particular beam is L, then if you go through the shear force diagram of this particular beam, then if you find the reactions at the supports, now as 2 point loads are there at same distance from both supports, so the reactions at the support A and support B will be same, that will be W. And if you consider section in between A and C, and if you consider the left part of that section and the forces acting on that left part, then only this reaction will be acting there. So that magnitude will become W. And in between A to C there is no force, so it will be same. And similarly, if you consider a section in between that point D and point B, and if you consider the right part of the section, then at that particular position again the shear force due to the forces will be W. And in between C to D, if you consider section anywhere in between C and D, then if suppose we consider left part of it, then you have two forces. W is the reaction at A, which is upward, and external point load W at C. So if you take sum of that, then in between section C and D, if you consider left part of it, you have two forces W and are opposite to each other, so that will be 0. And again on right part, again that shear force will be 0 in between C and D. So if you draw that shear force diagram, it will be as shown in this figure 3.1b, and that is at A the shear force is W, at C shear force is W. In between C to D, the magnitude of shear force is 0, and in between D to B, again the magnitude of shear force is W. So if you go for calculation of bending moment, and if you draw a bending moment diagram, it will be something as shown in this figure 3.1c. Okay, so from A to C there is increase in the bending moment, and from D to B there is a decrease in the bending moment value. And as it is simply supported beam, at support A and support B, the magnitude of bending moment will be 0. And from C to D, anywhere, the magnitude of bending moment will be W multiplied by A, that is distance in between that force and the support. So, if you consider this diagram, bending moment diagram, in between C to D, that is pure bending case. So, the portion C to D of the simply supported beam, as shown in this figure 3.1a, is said to be under pure bending, as there exists no shear force in this portion. Now we will go through theory of simple bending or theory of pure bending. So this is a simply supported beam subjected to uniformly distributed load W units per meter throughout the span L. And let us say this is a cross section of that particular beam, and due to the externally applied forces, the deflected shape of the beam is as shown in this particular diagram. So let us say due to median, the deflection is as shown over here. So if the end sections of the straight beam are considered to remain plane, then the beam under the action of bending moment bends in such a way that the concave edge of the cross section undergoes compression and the convex edge that undergoes tension. So as what is shown over here in this figure, if this is the plane before the force, and after the application of the force the bending is taking place, the deflection is taking place, and this end section of the straight beam that remains plane, then it is subjected to the compressive stress at this position and the tensile stress at this particular position, and it is drawn in this diagram, which is called as the bending stress distribution diagram. So below this axis, then it is subjected to tension, and above this axis it is subjected to compression. And in case of the another beam, which is we have discussed in case of SFD and DMD, that is cantilever beam. In cantilever beam, that will be opposite to this case, that will be subjected to tension at the top and compression at the bottom. So there exists an internal surface at which the stress is zero, and it is known as neutral surface. So this surface over here is called as the neutral surface, and the axis obtained by intersection of the neutral surface and a cross section is known as neutral axis. So it is shown over here in cross section part. So this axis is perpendicular to the neutral surface, or this at the cross section, that it is called as neutral axis. The bending of the surface takes place about this axis. So whatsoever bending is taking place is about this neutral axis. Theory of simple bending is applicable to the beam subjected to simple or pure bending when the cross section is not subjected to shear force. So this already we have discussed in the case of the beam when it was subjected to 2 point loads. So in between those 2 point loads, it is not subjected to shear force. So that is what is pure bending, and this theory of simple bending is applicable to the beams subjected to pure bending case. So there are certain assumptions in theory of pure bending. So the first assumption is the material is homogeneous, isotropic, and it has same value of MoS modulus in tension and compression. The second assumption is transverse plane remains plane. So transverse planes remain plane and perpendicular to the neutral surface after bending. So what is shown in this diagram over here is this plane. That plane before bending it is plane, and after bending it is the plane and perpendicular to the neutral surface. So if you consider tangent of the neutral surface at this position over here, so that is perpendicular to that tangent. And whatsoever the diagram is drawn regarding red color, so that kind of deformation is not taking place. Whatsoever deformation is taking place, the transverse planes remain plane and perpendicular to the neutral surface after bending. The third assumption regarding the theory of simple bending is initially the beam is straight and all longitudinal filaments are bent into circular arcs. So what is shown over here is this is some part of the beam, and one section is over here and another section is at this position, and let us say this xx is the distance between those two sections under consideration. And if we consider this deflected shape of those sections in between those two sections, then everywhere this will be a circular arc, that will be deflected as a circular arc. And common center of curvature. So what is said is initially the beam is straight and all longitudinal filaments are bent into circular arcs with a common center of curvature, which is large as compared to the dimensions of the cross section. So if we consider the dimension of the cross section or depth of the cross section as compared to depth of the cross section, the radius of curvature is very long. The fourth assumption is the beam is symmetrical about a vertical longitudinal plane passing through vertical axis of symmetry for horizontal beam. And the fifth assumption is the stress is purely longitudinal and the stress concentration near the point loads. So if point loads are there, then the force is acting at a particular position, then at that particular point there will be stress concentration. So that stress concentration is neglected, and that is the assumption. So suppose of the complete beam, some part of that beam is considered, and let us say this is the first figure regarding that, and second figure is regarding the cross section of that beam, and this third diagram we will again discuss it afterwards. And this we have already discussed, that is radius of curvature and the angle at the center. So now let us go through few terminologies whatsoever we are considering further. So this capital R is regarding radius of curvature of a neutral surface, and theta is angle subtended by beam length at center of that curvature, and sigma is the longitudinal stress, m is bending moment at that particular cross section, xx is the original length. So if you go to first diagram, this part from this small x up to small x, so this is original length of this part, and this capital XX in this diagram is neutral surface of that beam, and along cross section this axis is the neutral axis of that beam. Then the filament of original length XX, so whatsoever is shown in this first diagram, that is XX is the original length at distance y from neutral axis. So this length is considered from neutral axis, and its distance from neutral axis is y, and it will be elongated due to external forces. It will be getting elongated in length AB, that is shown in fourth diagram. So that is from this point up to capital A up to capital B. So that is A to B, or AB is shown as length after elongation. Then strain, as you know that it is a change in length to original length. So strain change in length is AB minus XX. So AB is elongated length, XX is original length. So AB minus XX is change in length divided by original length. So that is XX. Now if we consider this deflected shape, then at this position the length AB will be related to this radius of curvature and angle subtended by the deflected beam up to center. So that distance AB will become R plus Y multiplied by theta. So that will be length AB, and in original case this XX is the length at the neutral axis or neutral surface. So that distance will become R into theta. So AB minus XX, that becomes R plus Y into theta, that is AB, and XX, that is R into theta divided by original. Again it is XX, so it is R into theta. So if we rewrite this equation, it becomes R into theta, Y into theta minus R into theta. So this R theta gets cancelled. So the remaining term is Y into theta divided by R into theta, and that theta also gets cancelled. So what remains is strain is equal to this Y divided by R. So again we are aware that stress is directly proportional to strain, or stress is equal to Young's modulus multiplied with strain. So strain can be written as sigma divided by E. So that capital E is Young's modulus and sigma is stress. So the relation we get is sigma divided by y is equal to E divided by R. So sigma is for stress, y is for the distance of that particular part from neutral axis, or distance of that position at which the stress is to be calculated, that is distance y from neutral axis. E is Young's modulus and R is radius of curvature of neutral surface. So now in these terms, E and R is constant. So what we can rewrite is sigma is directly proportional to y. So it gives the stress at a point is directly proportional to the distance from the neutral axis. So at a particular point, if y is the distance of that point from the neutral axis, then stress at that point is directly proportional to the distance from the neutral axis. So if we now consider delta A is element of cross-sectional area of a transverse plane, what is shown in this diagram. If we consider delta A is the elemental area of cross-section at distance y from the neutral axis, then for pure bending, net normal force on the cross-section must be 0. So what is meaning of that? Earlier we have discussed that beyond neutral axis at top, it will be subjected to, say, for example, if it is simply supported beam, a compressive stress. So due to compressive stress, over that particular area of cross section, we will be having force, which will be compressive force. And at the bottom of that neutral axis, if it is subjected to tensile stress, then due to tensile stress and that particular area of cross section on which that stress is getting developed, so that force will be tensile force. So for equilibrium internally, that compressive stress and tensile stress, if we sum it must also be equal to 0. So what is written is, if delta A is element of cross-sectional area of a transverse plane at a distance y from the neutral axis, the pure bending net for pure bending net normal force on the cross section must be 0. So if this is the case, then what is written is integral sigma into delta A. So now what we have is at the top of the neutral axis we have compressive forces, and at the bottom of the neutral axis we will be having tensile forces. So if we consider the stress acting at this area delta A, the force will be stress into area of cross section. So sigma into delta A is the force getting developed due to stress. And then if we consider this as origin and neutral axis is as origin, and let us say from neutral axis up to bottom part, bottommost point, the distance is say minus d by 2, and at the top let us say it is d by 2. So integral from minus d by 2 to plus d by 2 of this force must be equal to 0, for summation of forces must be equal to 0. So substituting that sigma, which we have already discussed, that sigma by y is equal to E by R. So if we substitute this sigma is equal to E by R into y, then the equation becomes E divided by R into y delta A must be equal to 0. So out of that, this E and R, these are the constants. So what it gives us, if we take it out, that E divided by R integral y delta A must be equal to 0. So if this is the case, then integral y delta A must be equal to 0. So it indicates that the neutral axis passes through the centroid of the section. So centroid is nothing but the neutral axis for the case of the theory of simple bending. So also what we can discuss is bending moment must be equal to movement of the normal forces about the neutral axis. So what is movement of the normal forces is over here beyond this neutral axis at the top, if it is subjected to compressive stress, and at bottom of the neutral axis if it is subjected to the tensile stress, then due to that stress and that area of cross section below the neutral axis, the force will be tensile force, and at the bottom, if we consider area beyond that neutral axis and the stress due to compression, the compressive force will be over there. Then these two forces, if they are equal and opposite, then they will be creating a couple, and that will be internal movement. And this internal movement and the bending moment due to externally applied force, that must be equal and opposite. So that capital M, that is bending moment due to externally applied forces, must be equal to integral sigma delta A into y. So sigma delta A is the force getting developed at that particular cross section, which is at a distance y from the neutral axis. So integral sigma delta A gives us total force getting developed, and its distance from neutral axis is y. So that gives us internal movement. So earlier what we have written is sigma is equal to E divided by R into y. So if we substitute it over here, so integral E divided by R into y, and delta A as it is, and this term y is as it is. So again E and R is constant, so if we take it out, so that equation becomes M is equal to E divided by R integral. Now these two y terms becomes y square delta A, and that integral y square delta A is moment of inertia. So what we get is M is equal to E divided by R into I. So what we can rewrite is M divided by I is equal to E divided by R. So this is second equation. So earlier equation with sigma was sigma divided by y is equal to E divided by R. So with these two equations, in general, what we can write for theory of simple bending is M by I is equal to sigma by y is equal to E divided by R. So now here M is the bending moment due to externally applied forces at that particular cross section where we are analyzing for the bending stresses, and I is moment of inertia of entire cross section about the neutral axis, and sigma is stress. It may be compressive stress or it may be a tensile stress at that particular position or at that particular point at which we are calculating that stress, and y is distance of that point from the neutral axis, and E is length modulus and R is radius of curvature. With this, we will go for further discussion regarding the section modulus. The ratio I divided by y, that is moment of inertia divided by distance from the neutral axis. If y is the farthest or the most distant point of the section from the neutral axis, it is called as section modulus. So I divided by y max is called as the section modulus. So that is Z is equal to I, that is about neutral axis, divided by y max. And one more term is M is equal to sigma into I divided by y. So if we consider Z, if we consider the section modulus, then maximum stress will be M divided by Z. So sigma max, maximum stress, will be at the section modulus Z. Another terminology is moment of resistance, MR. So the maximum bending moment which can be carried by a given section for a given maximum value of either tensile or compressive stress, or that is permissible stress, is known as moment of resistance. So the maximum bending moment which can be carried by the given section for a given maximum value of either tensile or compressive stress, which is permissible stress, that is called as moment of resistance of that particular beam. These few are the prerequisites for further calculations or for the numerical to be calculated. So this you have studied in course engineering mechanics. That was centroid of area, then neutral axis. So that we are going to discuss further. Moment of inertia, how to calculate moment of inertia of a particular cross section, and you also aware about parallel axis theorem. With this discussion, we will go through one simple numerical, and the statement of the numerical is something like this. Analyze the beam as shown in figure 3.3a and find maximum bending moment, and draw the bending stress distribution diagram, or it is also called as flexural stress distribution diagram. The cross section of the beam is as shown in this figure. So this is one diagram which is giving us the beam and the loading on the beam and the cross section. If we consider section somewhere in between, then it is a rectangular section as shown in this second diagram. So it is a simply supported beam subjected to UDL throughout. The magnitude of UDL is 25 kN per meter, and the span of the beam is 4 meter, and it is subjected to hinge support at A and roller support at B, and the cross section of that beam is as shown in this second figure, that is a rectangular cross section having width 100 millimeter and depth 250 millimeter. So if this is the case, then first of all it is asked to find the maximum bending moment. So you are aware that in case of a simply supported beam subjected to uniformly distributed load over entire span, the maximum bending moment will be at mid span, and it will be WL square by 8. So W here, small w stands for the magnitude of uniformly distributed load, and L is span of the beam, and the maximum bending moment will be WL square by 8. So simply supported beam subjected to UDL throughout the span, the maximum bending moment will be at mid span, and its magnitude will be WL square divided by 8. So if we use this equation, then maximum bending moment WL square divided by 8. So W value is 25 kilonewton per meter, and L span is 4 meter. So 25 into 4 square divided by 8, that gives us maximum bending moment value as 50 kilonewton meter. So for rectangular cross section, the moment of inertia will be about neutral axis, that is I is equal to BD cube divided by 12. So this you are aware about. So if it is a rectangular cross section, the moment of inertia about centroid is BD cube by 12. So with this, if we substitute those values, width is 100, depth is 250, so 100 into 250 cube divided by 12, that gives us moment of inertia about centroid as 130.21 into 10 to the power 6 millimeter to the power 4. So these two terms, B and D, they are in millimeter, so that unit for moment of inertia will be millimeter to the power 4. So now you are aware that the distance of neutral axis will be at center of the cross section, as it is a rectangular section. Then y becomes d divided by 2. So y top and y bottom, bottommost distance from neutral axis and topmost distance from neutral axis, that will be d divided by 2. So that is 250 divided by 2, and that gives 125 millimeter from bottom. So now if we use that equation, that is m by I is equal to sigma by y is equal to E by I. Now we need to consider first two terms. The third term is not required for the calculation of stress. So at top and bottom, as these two distances are same, 125 mm for bottom as well as at top, the stress value at top and bottom will be same. So sigma c for simply supported beam, the compressive stress will be at top and tensile stress will be at bottom. So that sigma c is equal to sigma t, and maximum bending moment we have calculated. So maximum bending moment into y divided by I. So y is taken on the left part of that equation. M by I is equal to sigma by y. So if we rewrite for sigma, it is sigma is equal to m by I into y. So again, if we substitute those values, m is 50 kilonewton meter. So that is converted into Newton mm. So you need to convert kilonewton to Newton. You need to multiply by 10 to the power 3. And again from meter to millimeter, again you need to multiply it by 1000. So it becomes 50 into 10 to the power 6 Newton millimeter is the maximum bending moment. And y, at top as well as at bottom. Y is 125 and divided by I value. So I, that is calculated as 130.21 into 10 to the power 6. So if you calculate it, it gives us the stress at top and stress at bottom, or compressive stress and tensile stress. Both are 48 Newton per mm square. And now if we draw that bending stress distribution diagram, so that diagram will be something as shown over here. So this is the position of the neutral axis where stress must be equal to 0, and at top it is subjected to compression and the magnitude is 48 Newton per mm square, and at bottom it is tensile stress and the magnitude is 48 Newton per mm square, and the variation of that bending stress that must be linear, okay, or it will be inclined straight line in between those 2 points. So with this numerical, again we are discussing a few terms related to bending moments in case of standard cases, or say general cases. So if you have a simply supported beam subjected to point load at midspan, then the maximum value of bending moment is WL divided by 4, or if it is P written in terms of P, that will be PL divided by 4. So that is case when it is simply supported beam subjected to point load at midspan. So similarly, now as what we have discussed in earlier numerical, is it is a simply supported beam subjected to UDL curve. So this we have discussed in module 2, that is SFD and DMD, that maximum bending moment will be at midspan and the value of that will be WL square divided by 8. So with this, if again there is a point load acting in between, if it is at not at midspan, if it is somewhere at distance A from say support A and distance B from support B, then maximum bending moment will be at the position where that point load is acting, and value of maximum bending moment will be WAB by L, or PAB divided by L. If that P is used for force, then the maximum bending moment will be at the point where that point load is acting, and the magnitude of maximum bending moment will be PAB divided by L. So these are 3 cases, and in cantilever beam, if it is subjected to point load at free end, then the maximum bending moment will be at fixed support, and the value of that will be W into L. That is in case of point load acting at free end. And also in case of cantilever beam subjected to UDL throughout at the fixed support, the maximum bending moment will be WL square divided by 2. So these 5 are the cases which you need to remember, that in case of simply supported beam subjected to point load at midspan, the value of maximum bending moment will be PL divided by 4, or WL divided by 4, and if it is subjected to UDL throughout, the maximum bending moment will be WL square divided by 8, again it will be at midspan. And in case of the point load which is at distance A from support A and at distance B from support B, that is WAB by L or PAB by L, that is the maximum bending moment at a position where that point load is acting. And in case of cantilever beam subjected to point load at free end, the maximum bending moment will be at fixed support, and that will be WL. And if it is subjected to UDL throughout, then the maximum bending moment is WL square divided by 2. So you need to remember all these cases for the further numerical point of view. So I am thankful to you all for this lecture. Thank you.